When we first talked about the index of refraction, I didn't tell you everything up front. The index of refraction, of course, depends on the material, but it also is a function of frequency. And that's the same thing as the color of the light. As a general rule, the index of refraction goes up as frequency goes up. If you look in the book, you'll see that you have, we said n equals 1.33 for water, which is pretty good. But actually, for red light at 660 nanometers, n is 1.331, while for violet light at 410 nanometers, it's 1.342. That's a small difference, but that same kind of difference in glass lets us use a prism to separate white light into the colors that make it up. N is larger for violet than it is for red, so that means it'll be bent to a greater angle, and that means this famous album cover is actually accurate, where the purple is on the lower side and the red's on the upper side. This is the same effect that gives us rainbows. If you look at this image from the book, you see why we see red at the top of the rainbow and violet at the bottom, because of the way the angles are bent and the direction we're looking. This assumes there's water in all these areas, which there is when there's a rainbow. This dependence of speed on frequency for sound or light is called dispersion, and it'll come back. This and total internal reflection are the reason diamonds seem very sparkly. If you think about the way they're usually cut, they have a whole lot of flat spots or facets on them. That means light can bounce around a lot before escaping, and the difference in index of refraction for the different colors is what splits them apart. So some of the little sparkles look yellowish when they hit your eye, and some look blue, green, whatever.